Oh, again, we start. Peter Manz, University of Harvard. So Peter is one of the experts in plasma governance in fusion context of mining plasmas. So he's going to talk to us as a model for the bifurcated I model agreement. So you allow us to ask you questions and I give you the floor. Thank you.
It's a pleasure for me to be here. I like this performance a lot, so my last attempt was 10 years ago, I guess. It's on the I mode, which is a kind of confinement regime, and it's a very special confinement regime. So I find it really difficult to make a point to astrophysics or something like that. But yeah, so it will be a little bit more confined fusion because the topic is already especially the topic is confined fusion. I tried to pick you up on different parts, but a little bit on the details because the topic is so difficult. The solution is so difficult. Focus on the bifurcated I mode regime. I put it in brackets because I don't think that's really a bifurcation, but we can also discuss it today. Yeah, and that's it. And I have my special thanks. So most of what I want to see happen. I'm working on all of these things together. This Tim I started in fact studying at university and then how our ways get those exams some External Institute of Plasma Physics in Garching and Aztec Upgrade. All the other people in fact mostly are also then from Aztec Upgrade besides Amanda Hubbard, who can say not directly for contribution to this work, but because he for discussions and for continuous support on yeah, that's it. So, down. So I start an introduction on the different kind of confinement regime. The most important for particular tokamats are the low confinement regime called L mode, the high confinement regime, H mode. And this is the other ones you usually know. And then there is one PPP, which is the I mode, which is not the intermediate confinement regime. I think of it's an improved L mode confinement regime. So it's in principle. And the main part of the talk will be that on this proposed physical mechanism, how the line works. And then I had at the end some kind of postcard physics example where we had a lot of nice figures. The time it's not allowing it, but I can. So I will now start this introduction into H mode and I mode, and then tokamats is very important that you get good fusion performance. And you get a good fusion performance if you get a high temperature, because you need the high temperature to overcome the cooling barrier, and you need a high density, then you get high enough density. And important is the overall. So the overall performance, so here is shown the pressure, density times the temperature, and the line average quantity would be the one which you maximize. So if you do something now on the performance, if you want to improve the confinement, you can do this by getting transport barrier. Very important one would be if you have a transport barrier, it's the edge. This here is the edge transport barrier, and this can happen by the turbulence itself. So you can generate this edge transfer barriers, or you can use this by external shear flow. So usually it's the shear flow which is the turbulence, and then you get a reduction of the turbulent transport, and in particular steepening of the gradient. This is happening in the edge. And then in the confined region, the gradients are rather similar. This is due to the gradients before, which usually leads us to transport properties. Is very difficult to do something like that one. And the internal transport barriers also, but there it is not really continuously. This is I focus now mainly on the edge, and this is now what makes a difference here. So there's the appearance of this transport area, and then this everything sits here is on this point, and this is also pedestal. And this happens now above a critical heating power. So you have a low heating power, you increase the heating power, and at some point, boom, you are in this good temperature. Pedestal. At the same time, you observe the shear flows. So here is shown perpendicular velocity, and you can see that the velocity is steepening if you go to the edge mode. This has to do also with force balance. In fact, it's radial force balance because the vector field. So in the plasma, the flow is given by the speed velocity, so radial electricity at the edge determined by the diameter of the velocity. So the ion pressure, because here the also the electron pressure, the ion pressure, speaking stuff, you have to increase the pressure gradient, so the enhancement of the flow. But this can also happen in theory. Most importantly, it's not just that you get an increase in the flow, but that you have a different flow. So from different radial positions, you can have different velocities. So you can also always extract the background velocity from does not matter. So then we would have here radial shear flow, and these shear flows are known that they can suppress turbulence in this 2D turbulent situation which we face on the conduction. Therefore, there's a strong increase in the shear flow, which is solved to reduce the turbulence and allows to get the pressure load. You also see the reduction in time. So here you see the turbulence. So the color coded is the amplitude of the turbulence. If it's more red, we have a higher amplitude. If it's more blue, we have a lower amplitude. And you observe here now broadband turbulence in N mode. Then there's a reduction in the turbulence level and then so this is how you get different scenarios. Later, in H mode, you see that there are some spikes. So it's shown here in the signal from alpha. This is the mercurium alpha line. This is the radiation. It's radiating because you have the hot plasma you would not see, and if it moves out into the outer region of the machine, then it's interacting with neutrals. So because of that, you see that you have enhanced light, because you have enhanced neutral interaction with the plasma. You get that one if you have more plasma transport into the outer. You see in L mode, you have a higher level, and this drops. This drop is usually the one for how you identify the transition. And then later you take these spikes back. So you overall get also the transport. And these events are called edge localized growth because they're here at the edge and they do a lot of transport. So in between you have a low transport, and then during the events you have side transport. These edge modes, or that is the relaxation events, this figure how it looks like. It has a very filamentary structure all around the turbos, and they appear due to different aerodynamic instabilities. It's usually thought to be explained by a people unit mode. I would not know explain it, but just for your information. And this leads to the point that the gradients do not get arbitrary. Because you would have a reduction of the turbulence level, or the gradient steepness, you would steepen up the equation. Perfectly good for timing, but no, then at some point you get these instabilities, which will always relax the pedestal and the gradients. You also see how this works in time. Before the end, during the end, disappearing. If you see it before it's the pedestal, it's very steep region, and then it relaxes, and then after some time, it's steepening again. And the main problem is that now if you do scalings on these ends, you can project the heating power or the heat flux which comes through the outer parts of the plasma collimator. And this provide now the heating power would be 10 to 30 megajoule per cubic meter, which is a factor 2. Adds the factor is a factor 3 plus the material energy devices with it. So the main problem is that you cannot work with nice edge mode conditions. It's impossible because you will get the ends will destroy the diverter, and so it's not possible. Also, even heat flux is too high, because the prevalence is also kill the diverter. So there's no possibility of that to run in high confinement mode conditions in the typical high one. So we would have to find a way to operate at a good confinement, but without these and this is the IMO confinement regime. So the IMO confinement regime appears in unfavorable configuration. So what does this mean? So there are several points where you can get earlier to high confinement. If you will find any kind of stalings, they are usually in the situation nice. So favorable configurations. If you put the diverter on top, it's the same magnetic field, change the magnetic field, or if you both operate with too much hydrogen, this will always the power you need to go into high confinement. So if you waste this power by some of these things, then you will come at a higher power. You would come into edge mode, and this would be still possible. But at the lower power, you can go into this regime, which is now called the I mode, which stands for improved L mode. And this has a really strange feature because here you see now conditions in black and L mode. You do not have a really strong pedestal in the temperature. It uses the pedestal only in edge mode conditions. And in blue is shown the edge mode, and here you see the pedestal. And in I mode, you have similar pedestal in the temperature. So you see the improvement. But in L mode, you get an improvement in high confinement mode, but the I mode is really close to the L mode. And so it's a little bit strange because you think, okay, if the shear flows are killing the turbulence, they kill the transport. How do they kill the transport only for the density, only for the part of the turbulence which is driving the heat, and not for that of the density. Otherwise, the I mode is N3, so this is the good part because the pressure gradient is not so strong, and therefore the ballooning drive is not so strong. It's really easy to understand that you do not get any kind of ends. And it has also another nice feature. This is a low impurity confinement time, so they do not have the impurities are not readily confined. This is particles are in fact not readily confined. This is an advantage because if you have a fusion reactor, it's generating helium, and you want to flush out the helium, you could use the ends, flush it out, but if you use it out and use the ends, then you need the confinement regime, which is also flushing out the impurities, and this is done by I mode, so it doesn't annual side impurity confinement time. Other ones, so the end in between ends, the N3 edge modes, which are so N3 edge modes, which have good confinement, they have good impurity confinement time, which is not good for a reactor, and this is also regime for against the alpha edge mode has also quite worse. Prominent feature, we wish to also identify the ion from the turbulence side following point. So this was the reason for the remote. This is shown here in the frequency spectrum with the spectrometry measurement. This is transition from L mode to I mode. I will go to this also a little bit later. And in L mode, the turbulence is rather broadband, so it's right. And then in I mode, it splits up into two regimes. So in between here, there's a reduction in the turbulence level. And then you have here enhanced turbulence in the frequency enhanced turbulence. That's two bands. The upper band is called the BT regime mode. Just the name. And this is a prominent feature you observe. You observe it always an I mode. This is H not right isolation. So one question will be why you get to this equilibrium. And this will be then the last part of the talk. There are also capacity relaxation events, but they are not safe. So this is my note on the bifurcation on the I mode. So you might think now how to identify the I mode when you get there. So this is an experimental trace to Mustang's upgrade. So point is the following. So there are the dead one is in takes into power. This is increased now stepwise to go here. So this is one kind of step. So the red one is for diagnostic purpose. Not so important. Then you see the density trace, and you do not see any kind of change here. So much. I now put here L mode, I mode. And why I did it is now the following. So it says that it should be in improved confinement regime. Confinement is measured in these machines by this range parameter for H98, which is scaling parameter for confinement time. And it's very obviously, in fact, that if you increase the heating power, you increase the confinement. So it's always happening. So if you make a heating value, you see, oh, you get improved confinement, it's here. So the main point is if you want to see that the confinement is improving, you do see the improvement of the confinement with the steps, but more important is if you see something which is changing. And here you see it's rather flat, and then you see at this point you get an improvement of the confinement, even if you do not change the heating power, and the times are also changing. No? Therefore, the real transition to I mode will be here at 1.2 seconds, and then you will see the improvement of the confinement and the transition from that to I mode. So this is a radial electric field from the background pressure gradient, which also shows a particular point how steep the gradient is. With the confinement, you do not see here a strong increase. You see the strong increase after 3.5 seconds, but this is very increase of the heating power. So with the transition to the beta confinement, you do not see here very, very strongly. I call this now the weak I mode, and this one is the I mode. Therefore, I do not think it's really a bifurcation. There's somehow a bifurcation in this H98 factor. If you want to, but in all of the other quantities that we are. Now, on the main ones, the L mode and the I mode, you know the spectrum density measured with spectrometry. In L mode, you have the third region, and then the overall behavior of the turbulence. And then in I mode, you see here a reduction in between, and then here this is bump. This is going to be the mode as you expect this. So this is rather obviously to see in both of. If I compare here's the I mode with the L mode here, there's a kind of low frequency oscillation which we thought shows very much similarities to geodesic acoustic modes. This appears here in the envelope of the density fluctuation. This is the way how to measure the velocity. And you observe this kind of mode here too, in I mode. So there is this. And this strangely also appears in the magnetic field fluctuation. Yes, and also one point. So in the magnetic field structure, it's an n equal 0 mode, so homogeneous field. In fact, it has an n equal 1 and n equal -1 sideband. The usual jump has an n equal 2, n equal 2 sideband, and it's already different. Typical jump, which I don't know why it is happening, but if I use the same diagnostic L mode for typical jumps, I see the n2 sideband, so it's at least different. So I get the typical results for all your collision. For I motor, this is a little bit strange. Now I want to compare with the weak I mode phase, so this short phase here after. Here the time is not so long, so the resolution I can never show much, so it looks not so nice here. And you see the reduction here too. Here's the remote enhancement part, but it's not so strong. You can see this kind of feature. You do not see the journey with acoustic mode and in the envelope, but you see it in the back. It's also not really done right. Yeah, so the signal is stronger in the envelope is also not typical. But the frequency is very dumb light and so on. So this can be discussed. There's also a mode which is close to the equilibrium mode in the magnetic, but this is not a equilibrium mode. We can do experiments and then change the frequency. They are not at the same point, even though most discharges still have the same frequency. So it's very difficult to say now if it's a bifurcation. I don't know if it's really bifurcation. I guess it's a trend and continuous change. So this is now my proposed mechanism of the I mode. So the main question for me is how can I decouple the particle transport, and then now what to go on fundamental levels, or I want to say on how is it generally the case. So if I do not do anything, just looking at the equation, what is the difference between the transport for the particles and what would be the transport for the heat? And then I can look at the equation and just look for terms which appear on the temperature, which do not appear on the density. So there is a difference which I find in the thermodynamics, and therefore I wanted to explain how thermodynamics now would be. So if I consider usually a kind of local perturbation in the density, then this local perturbation, because here you have more density and here you have less density, now the electrons will react on the pressure gradient. And so the electrons will now move to the other positions, and so you generate parallel currents. Yeah, like you would do in a drift wave mechanism usually. Yeah. And now the main point is that you have to balance the parallel gradient, because otherwise you cannot be drift wave. So you have to balance with some other current use balances. Or just looking for the parallel dynamics, you cannot use the diamagnetic one because it would be in the same state. Yeah. There would be the polarization current. So you would get in here the polarization current, parallel currents, and the balance current to state current. Another part is that these parallel currents they can introduce now kinetic activity because of the induction. And then if you take the induction into account, then you will get an alpha wave. If you do not take the induction into account, you get the now it's just how this will be on the parallel. And if you consider this on for the electrons, it's the same. So if you have the temperature fluctuation, of course, you can also feel it. The gradient here will generate the currents, yeah, just like not like diffusive process, like thermodiffusive process, the particles will be faster, they will move on the heat lines, and this is the gradient to the generated currents, they also generate. So typically this looks the same. The main difference is that with the particle dynamics of the transport, this is carried by the bulk of the Maxwell distributions, where always the part from which is carrying the heat conductor is carried by the faster electrons, not the really fast in the case, but the ones which are on the flank to the high velocity. And this means that your parallel transport for the electrons is faster because you use the faster electrons in the distribution. The reason is also conduction is done by by a higher moment, if you derive this from the kinetics, then you will see that you use a higher moment. Therefore, your perturbation, if you have a local one, for the temperature, is reduced much faster, always, in any situation. This is also why in any of your codes that you use, you will see that if you have the same density and temperature gradient, you have a lower temperature fluctuation rate. In any case, this is happening in usual situations. The proposal is that all what I have done is that this effect now is particularly strong. That's it. So the only thing is that now I get into a situation where my conduction is really more important. And the point is just you need a high temperature. You just need a high temperature because then if you have a higher temperature, the conduction gets more important. You have to use so yes, also the chance of temperature to cause 70 by 2 or so, you have higher temperature conduction is more important. You can also see this if you are in the better conditions, you see if your diverter is in the conductive regime or in the convective regime. After 40 electron volts at the average temperature, you are convective. If you are higher, you start to get conductive. What you now need is you need 70 electron volts or something like this on the separators, then you are really strong conductive. And then your temperature will start to develop different dynamics and density. The next point is that usually you do not reach this at end because then you are at natural because at high temperature you get into air. Then the main other trick is then just that you had to find somehow a way to raise the power threshold that you are allowed to be an L mode. That's it. Yes, it's an effective. It's the most important one. The rest is now just to show figures. So if there are no questions on that one, I would be happy to get that now here. So then I have to see. Here, then I need that. Need to pass. So you go usually around, have so you take electron position, you go around, you have 60 meters or something like the parallel length. On the other side, you have around 1, 2, 3 collisions. So 50 meters of yes, so now, this depends also on density. But you need low collisions. This is the trick. So if you have too high collisions, it's also a reason why you can only do it in low density. The biggest is it.
Well, I have a couple of questions. But on this particular, is this only for the total array of magnetic fluctuations?
Yes, which also points to follow. Because if you have magnetic fluctuations, the magnetic fluctuations they do transport by the displacement of straight lines. You have a really strong conduction on the parallel side, because the white that is not so strong. So if you increase the fluctuations and the temperature fluctuations. So they are very
Effectively, you counting on the magnetic fluctuation in some sense suppress the transport.
yes. No. No. I use a conduction to suppress the transport. And if I have magnetic fluctuation, that would enhance it. So I have the conduction, which it takes my temperature fluctuation down. And now the entire system. If there are magnetic fluctuations, they will be very dangerous for the system because it has a really high conduction. And if there are the magnetic fluctuations, they will be a lot of
But conduction can also actually actually weaken the effects of magnetic fluctuation. Conventional computing, because the conduction is such a correlation type.
But parallel conduction,
Yes, parallel.
yeah, you have a lower population time. But I don't think this is really. Um, so I find it now for me very important that I had to find a regime that this parallel dynamics is very important and not so very important. Because only if the parallel dynamics is the one which is determining the dynamics, then this effect will be particularly strong. If you have the most prominent instability you think of and you talk about action is usually the ion temperature gradient law driven by the curvature. So the curvature on this ion temperature gradient, here's more ion temperature, here's lower ion temperature, here's the curvature drive, because the curvature sets the diamagnetic the curvatures of the diamagnetic velocity if you want to, or you can also work with a single particle picture. The curvature will make charge separation. This charge separation will induce electric fields, and electric fields will push the instability. So this is a basic interchange mechanism. It also works with ion temperature. Main point is that if you have pressure gradients, you can easily compensate that with the parallel dynamics. The electrons can move parallelly and work against the charge separation. They can also cool temperature down. So you have the electrons that it moves here and they can cool the electrons. They can never cool the ions, and therefore you have always stronger effects on ion temperature gradients. Therefore, the ITG has a stronger impact of the curvature. This is the reason also why the ITG is going to be much stronger, because it can be compensated by the curvature. And if I'm in a really strong ITG regime, my parallel dynamics is not so important, and then I will not see the effect. So I would have to find a situation now where I do not have strong ITGs, and this is now important in that regime, because then the alpha will dominate, and then the coupling of the density and temperature will be possible. It would be not possible for an ITG if it's going to be strong. And this is also how I found it. I now will show the data in this simulation. I had no intent at all in fact in the iron simulations, because I thought it has to do with the upper sinusoidal data structure and such thing. This is geometry, and I just have to code which is circle. I would not ever have tried this. From the beginning, the point was that I use this on service, I do simulations for others, and then they gave me backbone parameters which have to be below ion temperature gradient. And then I made the simulation, and then I said, oh, this looks like this was then how I got set. But now I'm motivated by this is also realistic. So ion and temperatures are very similar. So core also in I mode, usually they have to do particularly the same value, because also for us this is now we are using yeah, so if you are obviously for second meters it might be differently, but for fusion cases it's really similar. In I mode it's shown also for applications and core ion temperatures are. In general, the ion temperatures are very differently as the centroelectrics. So if you are in the linear spectral layer, fast spectral layer one, you get ion temperature, which is roughly 3 times the electron temperature. And I wanted to back up this now with a lot of references, because of the but usually the ions are much hotter than the spectral. So if you know that your ion temperature and electron temperature is the same, the ion temperature is higher. On this point, because of continuity, I just say now it's a separate reference condition. I need a little bit higher ion temperature and electron temperature, because otherwise, with step, you get a higher ion temperature in the spectral layer, which I find completely unfair. therefore, this motivates me when I say that's the position. I have a higher eye temperature to electron temperature. And if the ion temperature here is higher, then the gradient is greater, and so naturally will be reflected. This is a measurement, this is a measurement, so this is a measurement. That is a measurement, but that one that's a separate measurement. I showed the one.
You know why partition pretty much we would have expected that within the course of the
Yeah, this is not so high partition that can show the standard picture. You can see Sunny D book also at this meeting not the same. So we are still in I mode, and I mode always still in low density. Because of the low density, the partition. And I need a high temperature to this maximum temperature. This is the one which I can show from the measurement, how the reflector would look like, and then we have here the electron temperature, which can be measured quite well because we have a lot of different diagnostics and time. Then you have these ion temperature measurements now done with charge exchange, and they get you two problems, and at the end you have huge error bars on the screen. So at the end I do not show this because we do not know where they are, we don't know how much they are. EBS is separate with there are no measurements. But then in these those of these separate because at the beginning the points should be the same, and then there's a tendency in that it's the same. This is why API discharges it's always like that. So there are points where you can say, okay, maybe they are the same. I cannot show directly. Yeah, up to this point they are still on the same error bars. But there's always a tendency that it's a different. I cannot, for example, not prove that this assumption. But if I use this assumptions, I have lower ion temperature gradient. So because the ion temperature gradient is not so strong, I get low ITG. I have a higher ion temperature to electron ratio. Also good because I'm going to use final values effect. There is a two effects by which ITG gets weaker, and this is now very helpful than project. This is a code which I use for the simulation. It's a Java fluid code that we start. Uses circular geometry, and this is the reason why I think I wanted to use it for high mode because we know it in this part. Yeah, and then it sets different kind of moments. So here's there are always two equations for the lines, so for different species. So this is the density, affection of the density, and there's the gyro order term here. So this is for the first moment from the gyro moment, the second moment for the gyro moment. Calculate that one, parallel motion, curvature terms. Here is an equation for the parallel motion of the reflection between ones, parallel motion, curvature terms, one equation. Get for the dissipation which we want to and one for the temperature because the gyrosphere is parallel to the perpendicular temperature. Convection again and so on. Yeah, then there is the heat conduction, and heat conduction with 4 moments with parallel. Perpendicular one, perpendicular parallel, perpendicular, and so on. And the one here is only from the parallel one because so it's parallel, it's parallel, if it's perpendicular, it's parallel, perpendicular. I don't know, it's PowerPoint, I don't know if that's good. Or probably, yes.
Is that better? What do you want to know, Dominique?
Give him an exam on the equations. We can already see that you don't have to see the number.
But I might suggest that, for very technical questions like that, maybe you wait until the end and then you get the full-blown equations. These are supposed to be the gyro fluid equations that you get from the full-blown gyrokinetic system. You project them, you have them in the parallel and in the perp. You have the three first moments and off you go. And it's kind of, yes, plus collisions. So in some sense, I would say this is quite standard, and at least if there are questions, they're probably not on the equations themselves.
Okay. Yeah, this is a different transfer for moments. So there would be no flowing fluid. This is coming from the thermodynamic equation, which now relates the entropy temperature at intersect with the gyro moment, with the potential, and from there on. This is in equilibrium itself, which fulfills this Markov equation. So that also if you have fluctuations, the changes in the axis and so on. So for some parts it's quite nice and practical, but it's because of the analytic solution of the Markov equation in circular geometry. Also boundaries to circular geometry, there's nothing we can do. In fact, on that one, so I did not be able to. Even so, also, ever abilities.
You don't use fancy process things like
yeah, production is here inside because I started and simulated this. Production is still in the density, temperature, conduction.
Always no original type of progress like
No, I guess it is not. So this involves that, as I know, then the next gyro moment and the next gyro moment is 0. I said I just next moment is 0. This one will be used for the third one is now 0. Because in the article of the quantity channel, it should be used because otherwise. Depends what you say is emotional. Well, barrier state, make it clear boundary, and the threshold, and make it a clear something that has happened to the verification. The transition time depending more on the threshold. So I can make cases which look elbow-like, and I can make cases which And I cannot pass within one run. It is impossible. It is impossible because there are several kinds of parameters you will have here to control this, and these parameters are not allowed to change so much because it's a data state. You wouldn't could have because the kernel data is not allowed to change so much and so on. It's but I can have cases with a higher or the basic, but during one.
The sound system is not working as it should be, so people are complaining that it's not
Okay. Okay. Yeah. So here now enlarge, yeah. So this is now 0.24 part enlarge. What I just here want to say is the difference here in both, which I would also have at the fluid stream. So I have here my density, there's a parallel change here in these two species. I had this also in the temperature, but then there's a parallel change. And therefore, because this is included in the code, it should be possible to say this. It would be not included because I use the fluid code. Gyro fluid codes are also, they stop with the temperature or they stop with the density already. Then you have just one moment, for example, then you would not see this. But because you're in parallel, this parallel one is included, you would be able. These are the simulation results for how I could do this. So there are two different cases, which are only the only thing which are changes in fact the electron temperature, my reference electron temperatures, and the code developed because it's global, so I cannot not change so much afterwards the result. Also, that the density and temperature, the density, for example, should be the same, it's the same input parameters, but they change a little bit because the code is evolving, because it has to find it. And then the temperature in fact is changing, and you can see that the temperature is deeper if I have a higher temperature. So my main thing is conduction. I took now two cases which are more or less exactly the same particle flux. So I do not have, I cannot push this, so I do more simulations and get them with different particle fluxes. Now I now show two cases which have roughly the same particle flux. They have a different beginning flux, and I calculate the data back, and I get 1.6 megawatt for that curve and 2.7 megawatt for weekend flux. And they still have a very similar density gradient, and you see in the experiment also that it's ideally only the same. So you always see a little bit steeper density gradient and higher density to the NIMO. So I do not worry about this. And I would now calculate the effective dissipation by the terminal conductivity divided by the effective growth rate I calculate from this, which now changes from 2%, which is now the part of the growth rate which gets absorbed by the parallel conduction, 14%, so 5%. And increase in that one, and so on. So you can see that it's changing from nothing to something which has it. And then in the code you see, in fact, the appearance of the equilibrium mode that you do the frequency spectra. So before it's rather flat and traces power law behavior, and you see the reduction in the pump. This looks very similar. This is also what I have done for Astex, and then I'll do something similar for Alcatraz mode, because Alcatraz mode has also a lot. So here I do also the same. So these are all simulations of the particle flux, but now with the heating power. So 0.5, 1.2, 2 megawatt, and 6 megawatt, and so on. This is now the different cases, and then there's a low power. This is not so much, and then up. yeah, and all of these simulations are in fact for the previous one is an enhanced electron temperature, and then rather for time temperature. Now, if I go bifurcated heating power, which is so I cannot do this in 1-1 because it's not possible. That I can see the transition from case to case. Then I see that the density profile still does not change so much in terms against the temperature value. You can see it's keeping mostly on the electron temperature value. Then I can look now for signs and you can also already argue that this one is a bit more. But clearly it's essentially that we walk band, and then you can see strong periods of this period, how to shift it, and if you would look for alkali at this point, the frequency difference. You also observe in this geodesic acoustic mode. At the beginning, in this A mode phase, you do not observe this. And then in the cases where you have really low power, you observe here the geodesic acoustic mode. There's a low frequency range. It's also found now similar to the frequencies they observe in Alcatraz. And then the geodesic acoustic mode disappears if you go to higher powers. So this also looks like in the experimental part, which then we learn from Alcatraz. So this looks much how this looks in the simulation. Even so, I have a really unrealistic simulation because I'm circular, and I would not expect even this structure. Yeah, so also the frequency and so on, is roughly really nice.
What would be the weight number for the WP?
Yeah, also this is roughly the same in Alcatraz and Aztecs. In fact, we are now in the simulation wave number space. You would not see much of a difference. It's 0.0s 0.1 to 0.3. So roughly this. So again, and this is the quantity I said before, which I calculated. Then the parallel derivative of the parallel heat conduction multiplied with the temperature to get the energy, and then here divided by the temperature fluctuation, which is somehow now a growth rate or a rate on modification, which I now do for the Alcatraz scan. For the Aztecs one, I have just 2 points, so it does not look so nice. And then you can see this decreasing from 70. The values are really low because of the you see that the gradients are increasing, but they are not so strong. There's a comparison against non-linear growth rate, which is higher, and then at some point it's also increasing up, and then you can calculate how much percentage that you see. Very similar in fact to the aspect space, but in general, you see at the beginning, the tendency is in fact that you can see which is higher, and at the end, it's not helping anymore, so to reduce the fluctuation level, so it's more or less compensating the cost. So at the beginning, it's helping that you get a lower fluctuation level, but at the end, it's just compensating the growth of the enhanced gradient, because you have enhancing the gradient, so it gets steeper. Also, the transport gets steeper. In fact, you have a higher transport in general. Often people think if you go to improved confinement, your transport goes down. It's not true. You have higher heating power in improved confinement regime, so you have higher turbulent transport in absolute numbers. So your transport is higher in high confinement, only in normalized quantities you get lower ones. This because of the improved confinement smaller gradients, you have a whole higher growth rate and somehow compensated by that. And in general, also recent simulations from about first simulations, which are done for east, in fact, they use people remote, and they identify it as a drift alpine wave, which would now fit to my picture because this effect is related to drift alpine waves. Because only if the parallel dynamics is important, the conduction is important, and so on. And so So this now again two cases from us as I showed before, where you see the cross phase between potential density and then the cross phase between potential electron temperature shown over the wave number space. And if it's red, you have more power. The power here, which is now P over K1, this is from the final Lambda sequence. And so this does not measure any transport, because then the phase shift is also in the way that it does not. This rather continuous, so this would be my mode-like case here. And in this mode-like case, I have a force phase here at this point, which is above the P force, which is then here, this is different regime, this is the interchange regime. So I'm here in the interchange regime and I do my transport. And if I increase this temperature, then this drops down and then I have my power at this point. So this is one thing we change, and this is because your electrons can react better on the charge separation. They reduce the charge separation and they'll put it more into drift wave regime. Also, if you want to, you can calculate from the collisionality, your collisionality goes lower, so the electrons are not so hampered and so on. Yeah, the same in general, the temperature, so also this case. But it's going not that much down in temperature because the temperature itself induces a non-adiabatic response. In fact, you can see there's an effect too. So this will increase the cross phase of the density of the temperature compared to the density. That's the effect. So in N mode, the cross phases are very similar also. They are very similar. You can put the figures here one onto the other. They are really the same. And here now you see the difference. So the cross phase decouples. So if you increase the temperature, density, temperature, cross phases decouples, and then you can see the particle decouples. So at some point, you know. This one here is now in the drift wave regime. I can also show you other parts are more in the drift wave regime. And if I can also show this inductives, and I can show more. This and yeah, also I said already, the cross phase between the potential and temperature. Now, if you compare both of them, you see a higher, and this is due to the conduction velocity addition. Why it's not broadband? That's because here this one slide. So if you see here this line, you compare this to that one, signs at high, a really low wave number, so large scales, they get widened. Also the phase, for example, here, but the main part is the line. So I get the phase randomization effect, and the phase randomization effect, because then it has a wider distribution, allows for more different cross phases. So this means that the modes, they are not coupled always to the same partners, they now do whatever as they want, and therefore they do not do a lot of transport. So if you would be, for example, completely random, you would not see any transport because you would just have random fluctuations, and because you spread now in wave number space, the cross phase distribution, it does not have a strong effect. Then it comes to rest. Because if you do not have a strong coherency in the cross phase, and if you have a not localized cross phase, then the transport of these scales is lower. If the transport of these scales is lower, there's no energy input, therefore it lost coherency again. So this is things which are happening in this parts. So you just have, so then, yeah, because the coherence is reduced and the cross phase is not localized, you do not get into appropriate region. So I thought a long time that's due to additional magnetic fluctuations, which could induce that one, because you have your parallel electron motion, and then if you have magnetic fluctuations, then they will not be at the same point. Yeah, the MHE is a subset, so you can, if you put the potential fluctuation to maximum, and then some would drop out. So for example, in fact, what would drop out is the density would drop out. It's an yeah, the gyro fluid set, so the MHD would be subset.
That's why I asked you earlier about the magnetic right? That becomes the house of cards, right? That becomes some condition
I did not know how to quantify this. This is my main problem. I thought about that. You will see later that I had the idea on the magnetic fluctuations too, but I do not know how to quantify this.
Well,
I see the phase. I see the phase randomization. This is one thing I see. I can also quantify how much phase randomization I would have for different ones. I can also plot this. It would work out. So I have done that one too. So the effect is increasing this plasma beta. If you want to, I did not look for fluctuation there. It's a beta parameter, yeah. Yeah, this is happening. So if I increase beta, I get a higher fluctuation level. But for example, I get also higher shear flows with plasma beta. If I increase it, so this has always this equilibrium. I get stronger equals P flows, for example, too. So this is I cannot tune this independently. And I also would change. So I do this for experimentalists, and for example, in Astes, you want always to have the 2.5 Tesla. I can do a beta scan, of course, and change, keep the collisionality the same. But then I would have situations where I would change the magnetic field or some other parameters, because you would to have all the dimensionless parameters constant, and for example I'm bound to a magnetic field because all the discharge is bound to a magnetic field. Then I do not have everything independent. Because I actually use this in fact still for service, for experimental support. There was an happening at the end. Equilibrium mode is a reminder of the Broadband spectrum. So this is the same. I just put this on the side because it's now what's yeah. So you see this equilibrium mode already before. So there's experimental time changes. So this is one where you have a transition from L mode to I mode. To get stationary I modes in Aztecs, we have now a heating scheme which now detects the plasma beta at some location, and then if the plasma beta is not as your desired value, then the NDI system will heat more or less, and so you can stay in I mode. Problem was already before we in Aztecs upward we could not stay in I mode. I mode was always just a short regime. You transit into I mode. Confinement was getting better, and then you always go into high confinement mode. So there were no stationary I modes in Aztecs possible. So you have now a system which is now going with the heating power down, that you can stay longer in I mode. And then you can also do transitions at points you want to have. This is the heating scheme, this is all of the pulses. This is density for control, the density and density gradients of the line. And then there's at the edge, that is the top value increasing the temperature, that you see the temperature is improving, that you get this value. And then the plasma flow energy is a value for confinement. Yeah, but it's in hand. Then you see here one trend, and then there's another trend, and therefore you say, okay, there's a change in confinement, therefore. Then there are different diagnostics here for measuring temperature and density fluctuations, and these are done with colloidal diffractometry where you have the reflectometry, you have different points, and then you use the coherent signal of those. And the other one is relation electron cyclotron emission, where you have an ECE diagnostic and also reflectometry, and you calculate the coherent fluctuations. This is also here from CET, And if you use these kinds of diagnostics, you always see before this mode, which is transition here, and the big lower frequency, which is then transient when going into the CI mode, which is here the VT coherent mode, or this here should be the VT coherent mode, and then there's this transition. This is the part where then they said, okay, the VT coherent mode is already there before. But you see this only in the diagnostics, which are only measure the coherent part of the fluctuations. The coherent part of the fluctuations always driving scale. Yeah. And so I just want to say here that it's in principle in line. So diagnostic is the main intensity, the coherent fluctuations. They measure this before. So they measure the driving range. This is the part of the spectrum which I said is the I mode data. And the drive increase in frequency is because of the enhanced Doppler shift, because you have a steeper electron gradients, and then this makes it better. If you would look in typical now here for the mode case before, you would also see a coherent part here. It has a similar wave number, and you would, if I would just look for the coherent part, I would just also see this. Because it's coherent. And why I was so clear that I thought myself that I get into I mode is an aspect. If you look at Doppler reflectometry, the time traces, usually you get very random turbulent behavior on all of the scales. And if you look on I mode, we observe the following: you get these steps here, and so intermittent fluctuations. And most of the time you get like nothing, and then you see bursts. In fact, it's bursts. They have the distance between the weakly coherent mode. This is how a time trace look like in these experiments. So it is not really broadband turbulence. This is how it looks now in the experiment and in the simulation now. It's also not broadband anymore. It also has these features. So you see here the spikes of magnetic densities there without different Doppler reflectometry. And then there are also often also these events which have these intermittent behavior, and then they show this in the simulation. And that was in fact the point where I think I have an I mode, because it's really strange, and it's usually do not look like usually the time traces look. And this is a very particular feature on the dynamics, and this is recovered by the simulation, and therefore I thought it has to be something. When I saw that one, then I said, okay, I have it. Even so, you might say, well, it's important for something or so. I think this is something really special, which is I do usually not see. It's also a little bit. So, sorry that one. This is the one of simulations which are not at the same particle, at the same particle flux, because I did not do this before, and yeah. But I might usually do this also. Now, these are simulations which are at the same density input parameters, but I did not check if they have the same particle. But I was asked, in fact, to say what's the role of it was the shear suppression, in fact, and now you will get a scan where I keep the density from the input parameters the same, which is increase. And now I increase the temperature gradient stepwise, in fact, to get from L mode to I mode. And then I show here how the electric field develops in the simulation. And in us, we have an L2H condition of 15 kilovolt per meter. So this is then from an L mode condition, which are in blue, to I mode, to deep I mode, close to an H mode. Frequency spectra in these simulations. Then I observe at the beginning that I do a pretty broadband, and I get first an increase in the fluctuation level. And this is because I increase the temperature gradient scalings, in fact, something like that. So at the beginning it's increasing, but stays in broadband conditions, and then this bifurcated mode develops in C. And then I get a stronger increase in the temperature gradient, and then the bifurcated mode gets really, really strong, and because it's really flat, and there's a hump, and then for higher values, then this collapses into temperature. It's a fluctuation that the first time. Here's shown now in red the shearing rate at the outer part, and here to here, and in megahertz and megahertz scale, and this one is the vorticity, absolute known and vorticity impact of the fluctuations. And now I would say the shear suppression is the eddy turnover rate. The eddy turnover rate would be, as the shearing rate would be larger than the eddy turnover rate, but this has a distribution. So there is a negative one, so I take the median. Here, as this value, this is the mean, the black curve, and this is the 59% value. And so in all rate numbers and A-mode conditions, the turnover rate is much higher than the shearing rate. Now with the simulations, I increase the shearing rate here, and you can see that still at the I-mode conditions, the turnover rate is much above the shearing rate. And if I now approach the last values and go closer to H mode, then at this point, already a lot of the fluctuation spectra would be suppressed. In fact, and if I exceed here and I only have 95% level here, the fluctuation level drops. So it drops really when I go with the shearing rate above the fluctuation level. This is in fact quite nice. I think, but for me it was also the point that the shear effects are really strong at the I to H transition and not so strong at the L to I mode transition. And I have some notes on these ETROs, the so-called edge temperature ring oscillations on east. The experimental figure. And then they also want to have stationary I mode conditions, and in these stationary I modes conditions, they had the gradient modulation. They do it somehow with the beams, or not so much in what they see at least is that they have temperature which is moving in the I direction, and fluctuations which are moving in the electron temperature direction. And the electron temperature fluctuations are all here in frequency so modulated by the nuclear mode. And this is also what you would see in aspects, in Doppler, so you get this. And this is modulated by the nuclear mode. So this is the same as these figures. And you see that it's alternating. So you see that you get electron turbulence, which is nuclear mode modulated, and then you see ion turbulence, electron turbulence, and so you get the sustainment. And I just want to say that it's very much on the mechanism, because you would have, if your ion temperature, if you're in the ITG regime, it would not allow these effects. Then your ion temperature gradient would be then too high, and in the electron regime, then you get into this regime. So it would be also, from my opinion,
the right hand side, that only right hand side, it looks like cyclic, right? Your fluctuation intensity increases in time, it goes up again. What is that? So it's because the angle is not stable, you keep going from time to time, or what's happening?
It's very fast. This is then on the nuclear mode frequency. So you have this burst in fact. So it's I would not think that this in back transition. So here I have more feeling that this is I mode, this is A mode, I mode, A mode, I mode, and so they keep it. It's a longer time. So it's just one of these bursts in fact in between. But I still have the problem that I would run in one of. So stationary is a problem. But yes, really fast. I guess the problem that during this burst, even here in this one, I get a little bit relaxation of the my gradients. Let me not come back. Okay. Okay, I just try to use that one here. So I want just to say on the operational space one thing. So I said I get the phase randomization. That could be in fact due to magnetic field stochastization. Then I would have plasma beta which has to exceed a certain value. In fact, to get into I mode because otherwise I would not get the phase randomization. And I would have electromagnetic transport driven by that. If I have too high plasma beta, then it would be not really nice. And I would be in edge mode condition. In fact, yeah, then I would also have only electromagnetic transport. So you can decide on which one, but I have the maximum beta. I have here these plots on the proportionality ion to electron temperature ratio from the standard book, which is changing with the density, and we would use this here at the density, so we would have a factor 2 justified. And this also the JPEG measured in efficiency, so the ion to electron temperature dependent on that temperature. So to get the ion to electron temperature ratio, I need a low collisionality, and therefore here would be IgG dominated, and this makes me box. Now, if I would have a box, I can do by power balance, this is fixed harm conduction, different kinds of power lines through my box. And then I would get, for example, these basket upgrade here my power against density, and I see that I get by far larger operational space, this magnetic field strength. And also I get higher density with magnetic field strength as this is usually observed for I mode. This is just this box. This box can be, I just draw it here. I do not know the numbers, so I just draw here that one as a box, and you can do it better. Just want to show then as a last point that the box might be not just a box, but it might be a triangle or something like this, but you would have to first have a motivation to start. And then I go through my conclusion. The last thing I did not show. I would draw now the numbers. So sorry for. This was anyhow. No. So it's my summary. The most important is thermal conduction. It has two important effects. It's decoupling the density and energy temperature fluctuation, and also decouples the electron and ion temperature close to the separatics because the equipartition is done by this. It's allowed if you have different kinds of rigid because of the conduction to do that. And then the transport reduction of the A to I transition is mainly due to the reduction of the ion temperature gradient, because if this one is not there, then you would get to this point. And the Wiki mode appears because the phase randomization is higher and lower wave numbers. I'm not sure why this is the effect of if this is to magnetic fluctuations, I do not know, but could be. And the Wiki mode was the part of the IFA part which is driving. And then, yeah, in principle, it's for sure a finite window in plasma vector and edge collisionality can explain dividing of the operational space, but the exact numbers for prediction, then you would have to do a positive window loops in detail. Thank you.
The question of seems to me the two physical effects, well, one is the other thing is the phase randomization. So begs the question of physical and rather than controlled fashion than RNP, where you simply let the stochasticity reduced by the RNP supplied phase randomization. And I might point out that, there are in the discussion of these two things, the CMOD group has noted there may be similarities between the ion mode and the RNP. For example, the asymmetry in the beacon particle transfer. Right? The the RNG compound, but not so much a strong degradation. Is this the same basic physics playing out in different ways? And could we use the RNG in a sense more control with those? We know the RNG randomizes things. There's these experiments on where they show the RNG clotted phosphates in the express and it shows the power threshold. So the LH trend, they never seen their node, they said. But I mean, could you use this as a tool to trigger the node?
So I have a little bit the problem that you would how to identify the animals. Yeah, this is a little bit the problem in operation space from around separatrix position look very similar indeed. They are also appearing at the same parameter space. The density is also pretty low if the RNP is working good. So of course you can always put RNPs on it. Yeah, but if you want to, yeah, in these regimes in assets, when you are in M-suppressed conditions, and yeah, the performance is similar in the confinement factors, the density is very similar, temperatures are similar. You do not have this weak equilibrium mode, so yeah. So if you would use the weak equilibrium mode as an identifier, as we had used it before, then I guess it's difficult.
Because most of the stuff that RNG is looking in going H mode. I don't think anyone look at this.
Yeah, can be also higher.
Give you a control now on the phase range. Here, the phase range is predicted. You don't really know what's doing it. There's some speculation of magnetic perturbations, and it must be related to data for obvious reasons, but beyond that, there isn't a story, you know.
Well, I know the space randomization, but was at least something.
From a computer, it must be that. Right?
No, but you can also, so I cannot measure the cross-phase distribution in fact, but you see the low coherence at least.
There should be if it's a magnetic fluctuation, there should be certain techniques. And then it's going to be what happens if the magnetic fluctuation is extremely.
Yeah, but they have also different mode numbers, yeah. So the external ones are pretty large, the internal ones are pretty low.
This is, are you stuck with Dunstan or is it broader? Or
Yeah, so
I
in
asked
A mode,
the same question at PPF, and she didn't know either.
in A mode, in A mode the
No,
confinement.
well, it's not, but that I know.
In A mode the factor 2 higher in fact. I just want to say that the Goldstein values there are if you can use your tomography system really nice. So you are all the database from Thomas Reich, which he had done before 2011 on Jet and so on. This is when you have really low density, because only at low density your tomography system could resolve this. So you are in, this is low density. In low density A modes, when your tomography system can do this, then you are factor 2 higher, and in I mode you are in between. You can also make a density scan. Then you can see in I mode that you really continuously move this factor 2.
Does the current scale of, say, those three
during their thought.
Yes. So
Yes or no?
yes, this factor. So you have basically you have this term included at least as if you want to scale. For example, if you do the colloidal magnetic field, yeah, and you change the colloidal magnetic field by a factor 2, then in I mode this will change the factor 2. Yes.
Ah, okay.
Yeah, I can check the magnetic energy, and I can also check the electromagnetic transport. And I do this. I can calculate that one, and I could now show correlation between the. So if I have a higher temperature, I will have a higher electromagnetic energy also included. And I had to look on this. I did not make the plot, but it was there. So, but it's obviously in fact that this would be higher. So I also have a higher plasma beta, and I have higher electromagnetic fluctuation levels if I have higher temperature, and if I have then here better confinement. But I do not know why I get the how particular the phase randomization comes from the magnetic field fluctuations. So I do not have a really idea on a really proof plot. So I can show correlations that this one goes up and that one goes up, that I could.
I have some basic question. So, the main difference between I and nature one is the favorable direction, and one is the unfavorable direction. But you gave us only the upper. I was in the different lower direction and the direction.
So the important part is if the ion dot d drift is pointing towards or away from the active diverter. So if you have the normal magnetic field configuration, it's usually negative p direction, then and you are lower signal, then you are in the favorable configuration. And if you then keep the magnetic field directions the same way and flip to the upper diverter, then you would go into unfavorable direction, and your L2H power threshold jumps a factor 2 higher.
The conduction. So, as far as I know, the conduction responding to the conduction. Instead of conduction, but next year, other, there's no future. So, I would hope and wait such.
So the temperature gradient would be the two parts in the conduction. One is then for the physical small scale fluctuations, and then the fluctuation level would be the gradient, because you would be on the field line and this would be your gradient, so this will be included. The other one is on how the decoupling on the temperature versus the separatrix would work. And if this would be your questions, and I would be not able to do this because I'm limiter configuration, and so this would not work. Therefore, I had to induce this artificially by increasing my ion temperature by a factor 2 and making the initial profile of the. So I just changed the boundary condition that I have a higher ion temperature to electron temperature on both of these sides, and then this will do the job. So this is artificially induced.
That's the conduction.
Because I have a too high temperature on the limiter, because my scale length is too short. I have in the simulation a too short connection length because I'm in this limiter configuration. Therefore, my temperature gradients from the boundary to the separatrix they do not build up as efficient as they would do in a diverter configuration. And then the temperature are the same. I do not get the temperature gradient, as you said, and then I do not get the, yeah, therefore I did this artificially and increase the temperature, electron temperature ratio. But you can do it better.
I was wondering, well, we showed at some point we compared the correlation function. Well, I was wondering what role plays the present Reynolds stresses in building up the radioelectric field on one hand, when it's shaped, and whether you observe some kind of reduction of this effect when going to higher beta. Something you investigated?
Yeah, not in this runs. Yeah. Not in this runs. Yeah. So there's an effect on the Reynolds stress. It's also particular. It's not deep. So in my case, the contribution from the Reynolds stress is always in the simulations significant. It's so still the ion gradient, which is the main part, but otherwise there are 30% or something like this from the polarization derived from the Reynolds stress for the. So this is quite strong. And this plasma beta, I guess it does not in percentage. I think it did not change.
How do you get people channel and not in the limit? That's, I think, the real point of that expression.
No, because
Your magnetic fluctuation shouldn't have an effect on the stress.
but compared to the background values.
Well, the question is, the prostate, you know. I say there are observations where they do the iron. That would like. That's really approximately this. How does it enter one but not the other?
Because other one is momentum transport, and
So it's not that simple, right?
the other one is heat transport. And the main part of this is now that this is in fact the idea is now that you have different kind of channels and they have different kind of transport. So before it was for me mainly the point that you said, okay, I reduce the turbulence, how can it be that you have it in one channel or the other, but the channels are also very, very differently.
Why doesn't it have an effect on
The-
parameter is choosing? How it fluctuates? What parameter?
And you always need the turbulent transport you need. In fact, in this simulation, because the only one which you have, yeah. So this is your heat. You put it on one side, you get it on the other side out. Yeah, the heat moves out. Yeah, and then in the square of layer part, it moves into the targets and so on. Yeah, because this is carried in fact usually only by the turbulent transport. The momentum is usually fixed by you have dissipation which comes from your viscosity. And
Driven by the same fluctuations as well as the you would expect in a sense the low instability less efficient when moving to high party can face in the sense, in the same spirit of the phase conjugation that we use then
in the case if you have stronger shock oscillation, okay. I can look at this in detail again because
Before that, we finish the discussion of the let's sample that. What time? Master speed?